The dark fluid hypothesis is one of the most fascinating and still speculative ideas in modern cosmology. It proposes that the two biggest mysteries of the universe, dark matter and dark energy, might not be separate things at all, but instead two faces of a single unknown substance, a dark fluid. To understand why this idea even exists, let's first recall the basics. Astronomers discovered that galaxies rotate too quickly for their visible matter alone to hold them together. Something unseen, dark matter, must be providing extra gravitational pull. Meanwhile, observations of distant supernovae revealed that the expansion of the universe is speeding up, not slowing down. This accelerating expansion is attributed to dark energy, a mysterious force that acts in opposition to gravity. Here's the strange part. Both of these phenomena involve things we cannot see or touch, neither emits or absorbs light, and their exact nature remains completely unknown. So scientists began to wonder, what if they are not separate entities at all? This is where the dark fluid hypothesis comes in. It suggests there is one exotic substance pervading the universe, which behaves like dark matter in some contexts, clumping and attracting mass, and like dark energy in others, causing expansion. Could a single fluid explain both the binding of galaxies and the cosmic push outward? Ask yourself this: do we really need two unknown things to explain the universe, when one might do? The appeal of the dark fluid idea is in its simplicity and elegance. It reflects a principle called Occam's razor, where the simplest explanation that fits all the facts is often preferred. Instead of inventing two different cosmic ingredients, perhaps we just misunderstood the behavior of a more fundamental entity. But what kind of substance could behave this way? One proposal is a scalar field, a type of energy field that can vary across space and time depending on its energy state. It could clump like dark matter or stretch space like dark energy. Another idea involves Chaplygin gas, a theoretical fluid with properties that transition from acting like matter to acting like vacuum energy over time. There is even a more radical suggestion. Maybe space-time itself has a quantum structure we do not yet understand, and what we call dark components are just emergent effects of a deeper, hidden geometry. However, there is a challenge. The mathematics of such unified models must match a wide variety of astronomical observations, from the motion of galaxies to the cosmic microwave background to the formation of galaxy clusters. So far, no dark fluid model fits all the data, as well as the standard LCDM model, which treats dark matter and dark energy as distinct components. Still, the idea is far from dead. It invites us to keep asking fundamental questions. Is our current division of the universe into known and dark parts an oversimplification? Could a unifying theory emerge that reshapes how we think about gravity, energy, and the structure of space? As physics moves toward a new understanding of quantum gravity and the fabric of space-time, the dark fluid hypothesis serves as a powerful reminder. What we observe may be only the shadow of a deeper, unified reality. Would you like a breakdown of the main competing dark fluid models, or how they differ from standard dark energy models in terms of cosmological evolution? In modern cosmology, about 95% of the universe is invisible and unexplained. 27% is dark matter and 68% is dark energy. Dark matter interacts via gravity, but not electromagnetically, making it detectable only through gravitational lensing or galactic rotation curves. Dark energy behaves oppositely. It causes repulsive acceleration and explains why the universe's expansion is speeding up. Though both were discovered through astrophysical observations, they are modeled separately, with different physical assumptions. But what if they are just two manifestations of the same substance behaving differently across scales or densities? Galaxy rotation curves and cosmic microwave background, CMB, data require dark matter, supernova observations require dark energy. It's like hearing thunder and seeing lightning and assuming two storms until you realize they are caused by the same process. The dark fluid hypothesis proposes a single exotic field or fluid with properties that vary based on local conditions. In dense regions, like galaxies, it behaves like dark matter, clumping and exerting gravitational pull. In large-scale regions like intergalactic voids, it behaves like dark energy, causing space-time to expand. Such a fluid would require a non-standard equation of state, a relationship between pressure and energy density that changes over time, or this fluid would be neither gas, liquid, nor plasma, but something entirely beyond the standard model. The Chaplygin gas model attempts to capture this dual behavior through a single scalar field. It's like a strange material that turns solid under pressure and evaporates in a vacuum. Depending on the environment, it acts completely differently. Dark fluid models are often formulated using scalar fields, mathematical constructs similar to the Higgs field, where each point in space is assigned a value. These fields can be designed to evolve dynamically, switching roles between attraction and repulsion, depending on cosmological parameters like scale factor or energy density. Some proposals use k-essence, a scalar field with non-kinetical kinetic terms, allowing pressure to depend non-linearly on motion. Other models involve generalized Chaplygin gases with specific equations of state that interpolate between dust, dark matter, and vacuum energy, dark energy. However, tuning these models to fit all observations without creating inconsistencies is a major challenge. In k-essence theories, the scalar field causes inflation in the early universe and behaves like dark energy today. Think of a chameleon fluid that changes color depending on the container's shape. It looks different, but it's always the same substance. For the dark fluid hypothesis to be valid, it must fit all key cosmological observations: CMB and isotropies, large-scale structure, gravitational lensing, and type A supernovae. Most current models can fit some, but not all, data points. For instance, a model may reproduce the accelerated expansion well, but fail to explain the exact behavior of galaxies. Furthermore, observations of galaxy clusters suggest a cold, collisionless component, dark matter-like, while large-scale data requires a smooth, isotropic pressure, dark energy-like. Precision measurements from missions like Planck, Euclid, and DESI help constrain these models by providing tighter bounds on dark fluid behavior. The Planck satellite data shows specific peaks in the CMB spectrum that are sensitive to the balance of matter and dark energy. It's like designing a Swiss Army knife. You want one tool that does everything, but it often ends up doing none of them perfectly. While the lambda cold dark matter LCDM model is highly successful, it has shortcomings that motivate unified theories. For example, LCDM introduces two distinct unknown entities, L and CDM, with no deeper physical explanation or connection. Additionally, small-scale problems like the core cust problem and missing satellite problem suggest that cold dark matter may not behave as cleanly as expected. The cosmological constant problem also arises: why is dark energy so small yet non-zero? Dark fluid models attempt to replace these ad hoc components with a single, self-existing field. The discrepancy between predicted and observed satellite galaxies in the Milky Way raises questions about CDM's structure formation. LCDM is like patching a boat with multiple mismatched materials. A unified dark fluid is an attempt to build it from one seamless design. Some speculative theories go even further, linking the dark fluid concept to quantum gravity. In certain formulations of loop quantum gravity or string theory, space itself may be emergent from deeper entangled fields that give rise to both geometry and matter. From this view, dark energy and dark matter could be macroscopic effects of the same underlying quantum structure. Concepts like entropic gravity or modified inertia, e.g. Mond extensions, have also been proposed to derive dark matter-like effects without invoking new particles. These ideas remain controversial, but show how the dark fluid idea intersects with foundational physics. Eric Vierlinde's entropic gravity proposes that what we see as dark matter arises from information theory and holographic principles. It's like mistaking the wind for a substance when it's really the result of deeper invisible forces in motion. Detection of a dark fluid would be indirect through its gravitational effects, cosmic microwave background shifts, or lensing anomalies. If dark matter and dark energy are different phases of the same field, there might be phase transitions in the early universe that left observable imprints. Alternatively, fluctuations in the fluid might lead to new types of cosmic structure or gravitational wave signatures. Some researchers have proposed using 21 cm surveys or galaxy rotation anomalies to probe whether dark matter behavior changes over cosmic time or in different environments. Laboratory detection remains speculative, as no non-gravitational interaction has yet been observed. Next-generation telescopes like the Vera Rubin Observatory aim to map billions of galaxies to trace dark matter dynamics. Detecting a dark fluid is like watching the ripples on a pond to infer the nature of an invisible wind above it. While elegant in concept, the dark fluid hypothesis faced strong skepticism. Critics argue that it replaces two unknowns with a more complex unknown, offering less predictive power. Many models lack strong theoretical motivation and require fine-tuning to fit the same data that LCDM already explains well. Others point out that merging two fundamentally different behaviors, attractive and repulsive, into one field stretches credibility without solid evidence. Nevertheless, the hypothesis remains valuable for pushing the boundaries of conventional thinking and stimulating new experiments. The Chaplygin gas model was ruled out by early CMB data, showing that even unified models must match precise cosmological measurements. The dark fluid idea is like a beautifully written theory with no experimental actors. It reads well, but lacks a cast on stage. The dark fluid hypothesis continues to intrigue cosmologists because it promises a simpler, more unified description of the cosmos. It aligns with the historical trend in physics of unifying seemingly separate forces, like electricity and magnetism, or space and time. Whether dark matter and dark energy are two faces of the same coin remains to be proven, but the idea represents a deep desire to simplify the universe's fundamental blueprint. Future telescopes, gravitational wave detectors, and quantum field theories may provide clues that help validate or falsify this elegant notion. Until then, the dark fluid remains a tantalizing possibility, speculative, constrained, and awaiting evidence. Unified field theories in the past, like Maxwell's electromagnetism, succeeded. Dark fluid proponents hope for a similar triumph. It is like chasing the horizon. Each step brings clarity, but the destination remains elusive.